So this will be the start of the lecture on Chapter 8, material in Chapter 18 of your textbook. Please be sure to read that material because the lecture notes are going to follow the discussion in this chapter fairly closely. And what we're going to do is to start with a relatively straightforward example of diffusion in one dimension, and we're going to solve a series of problems at steady state showing how to properly formulate boundary conditions, how to set up and solve important practical mass transfer problems with this simple starting result. We will also be showing you how to couple different types of mass transfer problems together to get an overall solution of practical importance. And by this I mean that we will couple microscopic mass transfer solutions together with macroscopic solutions in order to generate experimentally accessible and testable results. So the place we will start this with is shown on the next slide, and it is a central result for a binary system. That is a system that contains two components, and you'll find more information about this in your textbook, but essentially following up on our previous lectures, we can write the total molar flux of one compound in a mixture, say compound A, in a single direction. We'll only have one-dimensional diffusion here, so in the z direction for sake of argument. So NaZ will be the total molar flux of A in the z direction. We can always write that as the product of the molar concentration of A, in units, for example, of moles of A per liter of mixture, times the velocity of A in the z direction. And you'll see that that combination of variables, concentration times velocity, does in fact give units of flux, moles per square centimeter per second, for example. And the total molar flux of A relative to a fixed coordinate system depends upon diffusion. That's the first term, Fick's first law that's written here. C is the total molar concentration of the mixture, dAB is the diffusion coefficient, and dxa dz is the concentration gradient in compound A. And it also depends upon the convective term, which is written in this case by the mole fraction of A times the product of the flux of A, times the sum of the flux of A and B. One could write a similar expression for compound B and an expression for the molar flux of B. However, these, due to mass balance considerations, typically working with focusing on one component is sufficient to get a solution to the entire mass transfer problem. So, for example, once you know the concentration profile of A in a system of A and B, then by its very nature you know the concentration profile of B, because, for example, the mole fractions of A and B have to add up to 1. Now, very typically we're going to solve these mass balance or mass transfer problems for the concentration profile of a component in a system. This is not often what we're interested in a practical sense. Very typically what we can measure will be some measure of the total flux or the total amount of material that's been transferred through a system in a given amount of time. And those sorts of calculations typically come about by integrating the concentration profile over either space or time to calculate a quantity that's experimentally measurable. We'll see that in our first example that we're going to look at. It's not sufficient to have simply this expression for the flux in a binary system. We also need to couple that to a mass balance, and we'll use shell balances, which I believe you would have been exposed to perhaps certainly in chemical engineering as undergraduates. And we're going to just look at problems for the time being that are at steady state. And a general shell balance or mass balance over a thin region of space says that the rate of transfer of A into that shell minus the rate of transfer of A out of the shell plus the net rate of generation of A by homogeneous chemical reaction is equal to 0. That is, any molecules of A that come into our shell balance area have to either leave that or they have to be consumed or generated by homogeneous chemical reaction at steady state. Otherwise, if material, for example, of A is accumulating in the shell over time, then the problem is by definition not at steady state. And so with this result, we will go on now. We have our expression for the flux, we have the shell balance expression, and the last piece we need for any problems are the boundary conditions. And the differential equation for the mass balance is solved using a variety of common boundary conditions. For example, the concentration of a component at a phase boundary, like a gas-liquid interface, may be specified. Typically, thermodynamics might govern the concentration, for example, of a gas dissolved in a liquid at a gas-liquid interface. Alternatively, the mass flux of a component or the ratio of mass fluxes of components at a surface can be specified. We'll see examples of that later. If the mass flux at a phase boundary, like a liquid-solid or liquid-gas interface, is controlled by a so-called boundary layer in the neighboring phase, then often the mass flux of A through that phase boundary is written in terms of a mass transfer coefficient, which I've written as K sub C here since it's based on molar concentration of A, times the concentration of A at the surface of the phase boundary minus the concentration of A in the bulk. We're going to talk in Chapter 20 more extensively about boundary layer theory and how you actually calculate these mass transfer coefficients, and so I'm going to put that discussion off in detail until then. Another situation that's very common for boundary conditions is that the rate of chemical reaction at a surface may be specified, and so for example, at heterogeneous catalyst particles, gas or components that come to a surface may undergo chemical reaction, and the net flux of a component to that surface may be driven by the rate of consumption of material at the surface at steady state. And so these three pieces of our problem-solving apparatus are applied to each and every problem that we're going to look at. We have the general expression for the mass flux that's given by the equation at the top of this slide. We have the shell balance that we put this mass flux expression into, and then we have the appropriate boundary conditions, and together then we can solve this for concentration profiles and then calculate rates of mass transfer and so forth. The first problem we'll look at is one that has been known for many decades, and that is a mechanism or a way in which diffusion coefficients can be measured, a so-called Stefan tube experiment. And in a Stefan tube experiment, you take a liquid, for example, I'm going to call it A, and put it in the bottom of a tube. You can imagine, for example, a graduated cylinder and putting a small amount of a liquid in the bottom of that tube, and then you pass a gas stream across the top of the tube, and as component A evaporates from the liquid phase, it diffuses through the gas phase up through the tube and then is swept away by the gas that's flowing over the top of the tube. It turns out that this is a very convenient way to actually measure the diffusion coefficients of component A in gas B, and we'll show how that falls out of the analysis. And in fact, this sort of a device has been used for that purpose. What you can imagine doing is, for example, taking a graduated cylinder with an amount of a liquid, for example, acetone, in it and exposing it to air or nitrogen, for example, blowing nitrogen across the top of that device, and then having the graduated cylinder sitting, for example, on a laboratory balance and just recording the weight of that graduated cylinder with compound A in it as a function of time. And as A evaporates, the weight will go down, and you can use that rate of mass change to calculate diffusion coefficients. Alternatively, you can measure the height of the liquid in this device as a function of time, and as that decreases, you can you can use that information to calculate diffusion coefficients. Okay, let's see how we go about this. We're going to consider this problem in the pseudo-steady state limit. That is, that the concentration profile of A in this gas phase establishes itself much faster than the rate at which the liquid A is depleted by evaporation. What you can imagine is over time, this problem really isn't at steady state. Over time, as the liquid level here of A drops, the diffusion path length increases, and the rate of evaporation of A must necessarily slow down because the distance that A has to travel through the tube gets longer as there's less and less A in the tube. The reason that this experiment works, and I'll show you when we develop a little more theoretical machinery later, is simply the fact that the diffusion coefficient, the concentration of A in the liquid phase is typically going to be at least 1,000 times greater than that in the gas phase. If you think about for example, the gas phase density of compounds relative to the liquid phase density, every time you have, for example, depleted the level of liquid A by 1 millimeter in this device, it means that roughly 1,000 millimeters of A, if you will, have had to move through the gas phase. And if this device is of any size that you would have, for example, in a typical laboratory, the time for that system to establish steady state in the gas phase is way faster than the time for which A depletes. And so we'll solve this gas phase diffusion problem in the limit of pseudo-steady state. That is a constant concentration profile in the gas phase between Z1, that's the liquid vapor interface, and Z2, that is the top of this tube beyond which all of the A is taken away by the stream of gas B that's blowing by. A consequence of this pseudo-steady state approximation is that the concentration, the flux of B in this tube is 0 under that approximation. Now, in fact, that's not quite true, because as the liquid level A is depleted, more B comes into the tube to displace it, and so the flux of B is very slowly changing in time. But for purposes of this analysis, we will set the flux of B to 0, and if we then go back to our molar flux expression and set the flux of B to 0, the result that we have is shown here. So we've simplified that molar flux expression. If we then apply the steady state shell balance between Z and Z plus delta Z, that yields the expression shown here in the middle, where the S is the cross-sectional surface area of this tube, and NA at Z is the flux of A entering that shell at Z, and NA at Z plus delta Z is the flux leaving at Z plus delta Z. There's no chemical reaction going on here, so this expression simply reduces to the fact that the flux of A entering at Z is equal to the flux of A leaving at Z plus delta Z. If that were not true, then you'd have accumulation of A inside the shell, and the problem would no longer be at steady state. And now we take the limit as delta Z goes to 0, and we get a classic result in mass transfer, that is that dNAZ dZ is equal to 0. That is, in one-dimensional binary diffusion, if the system is at steady state or pseudo-steady state, that is, the flux isn't changing with time, then the flux also doesn't change with position z. dNA z dz equals 0 means that the flux NA in the z direction is constant all along the gas phase region of this tube, and that result is absolutely independent of this problem. It's a very general result. It comes about because of two assumptions. One is that there's no chemical reaction. That's the right-hand side of this equation, then is 0, and that the problem is at pseudo-steady state. And in that limit, you get this result. We'll see this over and over throughout the semester. Now, we can take the flux expression we have, plug it into the mass balance as shown here, and what we need in order to solve for the concentration profile will be boundary conditions. Before we get into that, we assume that A and B forms an ideal gas mixture in the gas phase, so the gas phase concentration is given by the pressure divided by R times T. If pressure and temperature are changing negligibly in this system, then C is a constant, then that gas phase molar concentration is a constant. It can come outside the derivative. Also, the diffusion coefficient of A and B is typically a weak function of the composition of the gas mixture of A and B. And so, to a good approximation, the diffusion coefficient is constant and can also come outside the derivative. And with these simplifications, the mass balance is given by the expression shown here in the middle. We use boundary conditions that at the gas-liquid interface at Z1, XA is equal to XA1, and at the top of the tube, XA is equal to XA2. Often this value will be essentially 0, and XA1 will be given by thermodynamics, as we'll see here in a moment. And with these boundary conditions, we can solve this differential equation, and you should work this out for yourself to get the concentration profile of A that is shown here. Now, as I alluded to in the previous slide, the mole fraction of A in the gas phase at the gas-liquid interface is that given by thermodynamic equilibrium. And so we can write the concentration of A at the gas-liquid interface in the gas phase divided by the total molar concentration in the gas phase. This ratio is simply the mole fraction of A at that interface. And the concentration of A in the gas phase at the gas-liquid interface above a pure liquid A is given by ideal solution theory as just the vapor pressure of A divided by RT. This is essentially Raoult's law, if you will. And the total molar concentration in the gas phase for an ideal gas is just given by the total pressure over RT. And so that gas phase mole fraction of A at the liquid vapor interface is the vapor pressure of A divided by the total pressure. The vapor pressure of A is set largely by the temperature of the system, and so the way you manipulate the concentration of A in the gas phase, the gas-liquid interface, is basically by changing the temperature to change the vapor pressure, should you want to do so. Now we can also write the concentration profile in terms of the concentration profile of the inert gas B. That's just taking advantage of the fact that we know the mole fraction of XA from the expression here, and we know in a binary system that the mole fraction of A and B have to add up to 1, and so we can use the result on the previous slide to get the mole fraction written in terms of the mole fraction B. I'm going to integrate that expression over the entire length of the gas phase because it gives us a result that's going to be interesting and I think will be familiar to you. If you work through that integration, you'll find that the average concentration of B in that gas phase of that tube is given by what we have come to define in chemical engineering as the so-called log mean concentration average of B. That is the concentration of B or mole fraction of B at the top of the tube minus that at the liquid vapor interface divided by the logarithm of those two concentrations. And so you see here an example of how this log mean average falls falls out naturally from the solution to the mass transfer problem. And you see this over and over in other aspects of transport phenomena like heat transfer, and where the driving force for transport is often written in terms of log mean temperature differences. Now, we can go on to calculate the rate of mass transfer at the gas-liquid interface, which is essentially the rate of evaporation, by evaluating the flux. Now that we have the concentration profile, we can evaluate the flux wherever we want. We'll evaluate it at the gas-liquid interface. It would be the same throughout the gas phase of the tube. And so we're just going to plug in the concentration profile into this expression for the flux. The result is shown here. And we can write that in the following form that is more informative. That is, we can express it in terms of the log mean concentration of B, and in terms of the difference between XA1 and XA2, that is the mole fraction of A at the liquid vapor interface, minus the mole fraction of A at the top of the tube, divided by the length of the gas phase. And the thing that's interesting about this is if we go ahead and expand this, log mean term in a Taylor series, we can split this expression for the flux up into two pieces. The first piece over here on the left is the result that you would get if you had neglected convective mass transport effects entirely. So if we flip back briefly to our beginning equation for the mass flux, the first term here on the left-hand side represents diffusion. The second term represents convection. And in this particular problem, that convective effect gives us this 1 minus XA term in the denominator of the expression for the flux. And if we had simply neglected that 1 minus XA term that's shown here, then the solution to the differential equation would have looked like this. It would have been the molar concentration, the flux would have been the molar concentration times the diffusion coefficient of A and B times the concentration difference between the top and the bottom of the tube divided by the gas phase distance through the tube. This would also imply, if you work it backwards, if XA is negligible relative to 1, or if these convective effects are negligible, this would also imply a linear concentration profile throughout that tube. You can work backwards to see how that works. If further you recognize that the molar concentration times the mole fraction of A is just the molar concentration of A at the gas-liquid interface minus the molar concentration of A at the top of the tube, then this result becomes that the flux of A is equal to the diffusion coefficient times the concentration difference divided by the path length. This is a classic result in one-dimensional diffusion. That is, the flux is equal to the diffusion coefficient times delta C over delta Z. And now, not to neglect our friend the convection term, expanding this logarithm term for x sub b, you get the result that's shown here, and you should verify that. And so in cases where the mole fraction of A in the gas phase is small, one can expect these convective effects to be negligible and the flux to be given by the simple diffusion only result. And this is often the limit in which Stefan tubes are operated from a practical point of view. However, including the convection effects rigorously is very straightforward, as shown in the middle result here. Now, this result gives us the flux of A in the gas phase, and that is a start to connecting it back to a real experiment, but it's not the end. What we must recognize is in this experiment, what are the things that one could readily measure? And as we discussed at the beginning, things that you could readily measure is you could measure the mass of the entire system. If you had this this graduated cylinder with A in it sitting on a on a laboratory balance, you could measure the mass as a function of time, and watch as A evaporated, watch the mass of that system decrease. You could also measure the change in the height of the liquid with time, and I'll call that h, lowercase h of t. And that's what we're going to talk about now, is measurements where we measure that change in the height of the liquid A as a function of time, because this would be an experimentally accessible parameter that one could measure. And how does that depend? How does h of t then depend upon diffusion coefficients and the other parameters that we've been talking about? And this is the point where now we have to take our result for the flux, which is based on a microscopic analysis of the gas transport in the gas phase of that tube. We now have to couple that with a good old-fashioned macroscopic mass balance on the amount of A that is sitting in this tube as a function of time. And this is a situation which may be a little unfamiliar at first, but it makes good sense once you've done it a few times. So we've derived this equation for the flux of A in the gas phase under the assumption that the system is at steady state, or what we call pseudo-steady state. In order to write a mass balance on the amount of A that is in the tube and to track it versus time, we necessarily have to solve a transient problem. So we're coupling a transient macroscopic balance on the amount of liquid A in the tube with a microscopic steady state mass balance of A in the gas phase. And so let's see how that works here. And the reason that this analysis has value in a practical sense is that if the rate at which that gas phase concentration gradient takes to establish itself or to readjust to changes in liquid height, if that rate is really much smaller than the rate at which the liquid level changes, then this analysis is going to work just fine. And these Stefan tube problems are set up such that that is in fact the case. Another assumption that we've introduced here that I should mention is that the system is isothermal, and you can imagine that as liquid A evaporates, that does require energy, and so this liquid is always in thermal equilibrium with its surroundings. And you can imagine organizing the experiment such that you used a conductive, thin-walled, if you will, device for containing the liquid, that you had good convective stirring outside to maintain the temperature even right up to the surface of the device. And if you had a device that wasn't too big across, then you'd have good surface to volume thermal contact of the liquid with the surroundings, and that could be used to essentially make the temperature constant. And if the temperature doesn't vary, then that's the situation which we're analyzing this problem. And so what we rely on now is to couple our expression for the mass flux of A in the gas phase at the liquid vapor interface with an overall mass balance on liquid A in the tube over time. And what we're going to enforce is the following. We're going to say that any decrease in the amount of A in the liquid phase comes about because A has left in the gas phase. And so how do we write that decrease of A in the liquid phase? The way we're going to do that is shown here on the left-hand side of this equation. So if you think about it, the density of A in the liquid phase, rho superscript A, divided by the molecular weight of A is going to give the moles of A per unit volume in this liquid. And then we multiply by the rate of change of the volume of liquid with time. And that's just the surface area, the cross-sectional area of this device S, times the change in Z1 with T. Now, Z1 is going to decrease as time goes on, the way the coordinates are drawn, and so I put a minus sign out front to make this essentially the net amount of A that is put into the gas phase. And the amount of A that's put into the gas phase is by definition equal to the flux of A time in the gas phase times the cross-sectional surface area. And we've just written an expression for the flux of A in the gas phase on the previous slide, or we've just derived it. And so we can load that up here, and we now start to connect the change in the height of liquid, change in Z1 with T, with the gas phase concentration profile and the rate of mass transport in the gas phase. We can with a bit of algebra, you can see the relationships here between Z1 and H of T and capital H, which is the initial gas phase length in the tube at time T equals 0. And eventually, we can integrate the expression for Z1 over T, and we get an expression for how H of T, that is, how the distance from the initial starting point of the liquid level at time T equals 0, how that evolves in time. And I'll show you on the next slide a little bit more about that. The relationship is that if we look at the Z2 minus Z1 at any time, I can write that as Z2 minus Z1 at time T equal to 0 plus Z1 at time T equals 0 minus Z1 at time T equal to T, and we can express it in terms of H, that is Z2 minus Z1 at Z equals 0. This is capital H, and then this piece is lowercase h of T. And so we will replace in our flux expression Z2 minus Z1 at T with capital H plus lowercase h of T, because this is what we're going to measure experimentally, measure the rate at which, or measure the height of the liquid as a function, the change in the height of the liquid as a function of time. And the flux then is can be written as shown here. We can then isolate, if you will, the expression for H of T, or solve for H of T as we did on the previous slide. What this shows is that within the scope of this model, the flux of A at this liquid-vapor interface does slowly change with time. And the reason it changes with time is as time goes on, the distance of the gas phase, the length of the gas phase, if you will, increases. And as that length of the gas phase increases, the distance over which A has to diffuse under the same driving force increases, and that drives the flux down. Now, typically this experiment would be set up such that little h of T would be much less than capital H. That's by having capital H be larger than little h of T is during the duration of the experiment. And so from a practical matter, the flux can be regarded as essentially constant throughout this experiment if lowercase h of T is never very big relative to capital H. However, even if it is, you can account for that as shown here. Let me back up just to make one more point. You can imagine now, if you have data for the change in the height of the liquid as a function of time, you know what this, based on the way you set up the experiment, you'll know what capital H is. One will know the liquid phase density of A, that's rho sub A, its molecular weight. Based on the pressure and temperature, the molar concentration of A, the molar concentration of mixture C is just given by P over RT. We discussed calculating XA1 at the liquid-vapor interface based on the vapor pressure of A divided by RT, and typically XA2 is equal to 0. And so if you look at this expression and you had data for the disappearance, for the change in little h of T versus time, if you just took experimental data and measured h as a function of time, the only unknown in this expression would be the diffusion coefficient, DAB. And so if you make the measurement of the change in height of liquid as a function of time, All of the other variables here are fixed except DAB, and you could use that data then to extract the diffusion coefficient of A in B in the gas phase, and that's how a Stefan tube is used in a practical sense. Now, we'll go back and calculate the mass average velocity. I'll tie this into some of the fundamental concepts that we've been discussing in relation to convection and so forth. So we can calculate, by definition, the average velocity of A in the z direction is just the ratio of the flux divided by the molar concentration of A, and I can write that, if I wish, as the molar concentration of the mixture times the mole fraction of A at any position z. And the flux is a constant, so I'll just evaluate it at Z1 because I already have an expression for that. And so here's the expression for the average velocity of A in the z direction. And what you can see from this that is interesting is that as time marches on in this experiment, and Z1 of t goes down, the velocity of A slowly decreases. That reflects the slow decrease in the flux that we mentioned over on this expression. And you can also see that because there is a concentration gradient in A, that the velocity of A will change depending upon the height in the tube. However, the flux is constant, and so that must mean that the concentration of A on a molar basis is not changing. So the mole fraction of A will change slightly as you go up the tube because there is a concentration gradient in A, and that means that the molar concentration is adjusting to make that all constant. The mass average velocity for the entire system is defined as follows. This is a textbook definition of mass average velocity. It's the velocity of each component weighted by their mass fractions. We have assumed that the flux of B, that is the inert gas, is 0, so that term goes away, and we can write an expression for the mass average velocity that's shown here. It depends on the average molecular weight in the system and on the concentration difference as well as the height difference. What it says is, as long as there is any flux of component A, then there is a convective velocity. That is, there is a net motion in the center of mass of the gas phase relative to stationary coordinates. And you can imagine that this has to be the case because A is evaporating from the system, and so on average there is a drift of A convectively up through this tube brought about by diffusion. And so this is so-called, the reason there is a net overall velocity in the system, we call this a convection effect, but it's also referred to as a frame of reference effect, that the frame of reference that we picked for solving this problem is the laboratory fixed frame of reference, and the center of mass of the components in that gas phase are moving slightly with respect to that frame of reference. They have to in order for diffusion to be occurring. And so this term is not 0, even though diffusion is the only, molecular diffusion is the only mass transfer process that is operative here. Now I want to pass to a related problem, and that is diffusion through a stagnant film about a spherical particle, or if you will, a droplet, or a solid that is slowly sublime, a liquid that is evaporating into its surroundings, or a solid droplet, a solid sphere that is slowly subliming into surrounding quiescent gas phase. That would be the equivalent of what I call a mothball problem, where you hang a mothball up in a closet and it slowly sublimes into the surrounding gas phase. We're going to fix this problem fix it up a bit, because I'm going to compare it to the Stefan tube problem here momentarily. And the way we're going to do that is we're going to say that outside a a radius away from the center of this particle of R2, that the concentration of A is essentially constant. And we'll show that that's later that that's a reasonable consequence of boundary layer theory. And at R equals R1, we're going to impose thermodynamic equilibrium. And so the mole fraction of A in the gas phase at R equals R1 is going to be XA1, and beyond R equals R2, the mole fraction of A is XA2. And you'll see why we're going to do that when we connect this back up with the Stefan tube problem here momentarily. We're only going to consider the pseudo-steady state part of the problem. That is, we're not going to solve for the fact that as A evaporates from this liquid droplet or from or sublimes from a solid, that effectively the sphere is shrinking over time. But we're going to treat it first in a pseudo-steady state problem, and I think later, either in a homework assignment or something like that, you get the pleasure of coming back and doing the whole problem where you account for the decrease in the mass of the sphere with time as well, like as we'd done similarly in the 1D case or in the rectangular coordinate case with the Stefan tube. The expression for flux, which you'll find in your textbook, in the radial direction is exactly the same as it was in the linear or in the rectangular coordinate system. The only difference now is we've replaced Z with R. Some texts will automatically write the expression for the total flux as minus the diffusion coefficient times the gradient in the concentration in the radial dimension. And this is often a very good approximation if the temperature is constant, because the total concentration is often not changing very much, and so you can bring it inside this derivative with absolutely no problems. We're going to, just to add a little bit of further teaching to this example, we're going to consider a case where the temperature is varying as you go out radially from the surface of this droplet out to R2, and so we're not going to make that assumption and bring Ca into the derivative in this case, because we're going to keep it outside, because we're going to account for the temperature effects on both the diffusion coefficient and the molar concentration in the gas phase between R1 and R2. Now, we also write as we've done in the rectangular case with the Stefan tube a moment ago, we write a steady state shell mass balance between R and R plus dr, and then take the limit as delta R goes to 0. You may recognize this as the resulting endpoint of that shell mass balance. If not, please go back and refamiliarize yourself with shell balances in spherical coordinates. But essentially it says that unlike the rectangular case, where a consequence of being at steady state with no chemical reaction was that the flux of A in the z direction was 0, now it's R squared times the flux of A in the radial direction that's equal to 0. And I think that's a classic result for steady state mass transport without reaction, or even steady state heat transport. You find the same result if you were doing the analogous heat transfer problem, where instead of having mass flux here, you'd have the heat flux. So we then have our expression for flux. We have the shell mass balance that we can insert that expression into, and I promised that we would let the temperature vary radially, and I'll do that without getting too much into a heat transfer course. I'm going to just assume an arbitrary profile for the temperature in the radial direction. I'm not going to spend time justifying why this is so. It's a bit outside the scope of what I want to cover with you right now, but nevertheless, one could introduce a temperature profile into this analysis, and the temperature affects the diffusion coefficient and the total molar concentration. Diffusion coefficients typically vary approximately for gases as T to the 3/2 power. The concentration dependence of the molar concentration of an ideal gas is just given by P over RT. And so we're looking in our mass balance expression for the product of C times the diffusion coefficient. And so if the diffusion coefficient has this dependence on temperature and therefore on distance, then C has this dependence on temperature and thus distance. And we can introduce those approximations into the mass balance as shown here, where C1 is the molar concentration of the gas phase at R equal R1, and DAB1 is the diffusion coefficient of the gas phase at R equal to R1. And we can then solve this differential equation with the boundary conditions that we specified earlier, and the result is shown here. If there is no temperature dependence you have an isothermal case, then N in this case would just be set equal to 0. You can see that setting N equal to 0 here makes T independent of R. And so you recover the isothermal result, which we'll need in a moment, by simply setting N equal to 0. Typically what we're going to want is to use that concentration profile not as an end in itself, but as a means to calculate the flux. And now we'll calculate the flux at the sphere surface using our flux expression. Now with the concentration profile, we can evaluate this derivative. The result is given here. I won't belabor this except to say that typically what one would be interested in, if you had, for example, you had drops of a liquid that were evaporating into a gas, or if you had a solid sphere that were subliming into a gas, you'd be interested in what is the net rate at which I am adding component A, that is the component that is in the liquid or solid material here. What is the net rate that I'm adding that to the environment? And that net rate of transport of A, or conversion of A from the solid or liquid form to the gas form in terms of moles per unit time would be given by the flux at the particle surface times the area. And so at the pseudo-steady state analysis, the net transport of A, or the net amount of A that you're putting into the gas phase, is given by this expression. Now you could couple this with a mass balance around the particle itself and determine the time at which it would take for this particle to disappear based on these diffusion results. But again, I'm not going to cover that problem today. The reason that I wanted to put these two problems side by side is so that we could compare the Stefan tube result with the result now in spherical coordinates for evaporation of a droplet. And we're going to consider this now in the case where the temperature is isothermal. So I'm going to use the isothermal result for the mass flux of A in the spherical case, and that's recovered again just by setting N equal to 0 in this expression, because N was the exponent that was used to tell how fast temperature was changing radially. So when it's 0, you have the isothermal case. And so this is the flux at the liquid gas interface in the Stefan tube. This is the radial flux at the liquid or solid gas interface in the spherical case. And I can, similarly to the Stefan tube case, there's nothing that prevents me from introducing the log mean average of the inert gas B into the spherical result and rewriting that expression as shown here. There's absolutely no approximation in that. It's perfectly rigorous to do so. And what I'm aiming to do here is to make these two results look more and more alike, and to show under what circumstances this one-dimensional result can be used to approximate a problem in spherical coordinates. And so here is the result for both the rectangular coordinate case and also for the radial case. And I want to consider now the case where R2 minus R1, that is this layer around the liquid or solid droplet, when this layer thickness is thin relative to the radius of the particle r1. That is, I want to write r2. That is the radial coordinate at the outer band of where the concentration of A is changing in the gas phase. Remember, the assumption we made was that out beyond R2, the concentration of A no longer changes, and typically that would be brought about by stirring the gas phase around the particle, and this distance, the layer thickness here, would be called a boundary layer. We'll analyze that in more detail in Chapter 20. But we want to consider a case where this layer thickness, delta R, is less than R1, and in some cases maybe much less than R1. And so what I'm going to do is start with that spherical expression for the flux. I'm going to introduce for R2 that it's equal to R1 plus delta R, and that's what I've done here. And I algebraically manipulate that as shown here. And then if delta R, if the layer thickness, the gas layer thickness, is much less than the particle radius, we can expand 1 over 1 plus delta R over R1 in a Taylor series expansion as shown here. And if we keep only the linear term for the time being, then we can rewrite this expression as shown here, and it simplifies to the result that's shown on the right-hand side of this slide. Now, let's compare the Stefan tube result, that is in rectangular coordinates, with the result in spherical coordinates. And if the gas phase tube length, Z2 minus Z1, is considered to be analogous to the layer thickness, delta R, then these results are identical to one another. That is, the rate of mass transfer in the spherical case is exactly equal to the rate of mass transfer in the one-dimensional case. That is, you have gotten to a situation where, for all intents and purposes, from a mass transfer point of view, solving either the rectangular coordinate problem or the problem in spherical coordinates is exactly the same, and that occurs when this layer thickness R2 minus R1, or what we're calling delta R, when that is less than the particle radius. You might ask what would be the criteria for that, and the way you would, for when the rectangular solution is a good approximation in the spherical case, and the way you do that is you come back to the approximation we made to get there, where we expanded this term from the spherical case in a Taylor series expansion, and we got rid of everything after the linear term. And we could ask what would be the value of a parameter, of the parameter delta R over R1. What does that value have to be in order for make the linear term larger, let's say 10 times larger than the next term in the Taylor series? Now, I picked 10x here as an arbitrary factor. You could pick other values as you saw fit for a given problem or level of accuracy that you wanted. But we could ask, what is the criteria under which this linear term would be at least 10 times greater than the next term in the series? And you know the way this works is with the Taylor series expansion, delta R over R1 is less than 1. The next one is delta R over R1 squared, so that by necessity is a smaller term than this one. The next term will be delta R over R1 cubed, and that'll be smaller than this one, and so on and so forth. So if I compare just the linear term with the next term in the series, this will give us a good feeling for when the approximation is valid that lets us write this expression in a form that looks essentially the same as the rectangular coordinate or the 1D case. And the result from that comes out to be that if the layer thickness is less than about 20% of the radius of the particle, then we can use the diffusion solution in Cartesian coordinates as a good representation of the solution in spherical coordinates. This turns out to be important in, for example, gas phase catalytic reactors, where we have a reactive gas entering the end of a tube packed with a non-porous spherical particles that are coated with a catalyst. And at the particle surface, A is converted to, for example, B via heterogeneous catalytic reaction. As a first step towards modeling this, we analyze the mass transfer and reaction in the vicinity of one of these catalyst particles, and then we couple that to a macroscopic mass balance across a slice of the reactor between Z and Z plus delta Z to give a model of the performance of the whole device. So again, think back through all of the examples we've looked at, except for we didn't finish up the spherical case, but back to the Stefan tube, we couple a microscopic mass balance in the gas phase with a macroscopic balance to predict the performance of a device that can be measured. So very often in practical mass transfer problems, we're coupling this microscopic mass balance with a macroscopic solution as well to get device performance. And so around one of the spherical catalyst particles, there will typically only be a concentration gradient in a very thin layer next to the particle surface. I hope this is sounding familiar to the problem we just looked at. And at distances beyond this thin layer, which is the so-called boundary layer, the bulk flow of gas through the reactor forces the mixing of the gas from each particle to form a homogeneous and uniform bulk gas composition at that particular position Z in the reactor. And we'll learn in Chapter 20, when we study boundary layers, we'll learn how to predict the thickness of boundary layers and how to predict rates of mass transfer through boundary layers based on fundamental mass transfer concepts, typically dimensionless numbers like the Reynolds number is going to enter evaluation of the mass transfer coefficients in these cases, but we'll save that discussion till we get to Chapter 20. Because the boundary layer around that particle is thin relative to the size of the catalyst particle in typical practical circumstances, we use a 1D analysis to model a mass transfer, just a rectangular analysis to model a mass transfer between the catalyst particle surface, where the concentration of B, the product, is high, and the concentration of A, the reactant, is low, out to the edge of the boundary layer where the concentration of the product B is lower and the concentration of A, the reactant, is higher. And then at distances beyond the boundary layer, the reactor gas phase mixing forces the compositions to be homogeneous. We start with the expression for mass flux that we've been using all along today. And now we have a situation where we use the reaction kinetics at the catalytic surface to set the relationship between the fluxes of the components A and B. So A is only going to this surface because it's being consumed at the surface to produce B. And the rate of transport at steady state of A and B has to be linked by the stoichiometry of the reaction. So if we consider a dimerization reaction, for example, where two molecules of A at that catalytic surface combine to form one molecule of B, then at steady state, for every mole of B that leaves the catalyst surface and heads out towards the bulk gas, 2 moles of A must have diffused to the surface. And this is based simply on the reaction stoichiometry, and that stoichiometry then sets the relationship between the fluxes of A and B. And in this particular case, the flux of B is half the flux of A, because for every, you need to bring 2 moles of A in, so the flux of A has to be twice as high as the flux of B to make a mole of B. And the flux of B is in the opposite direction of A. B is coming in, B is going out rather, as A is coming in. And so at steady state, the flux of B is minus 1/2 the flux of A. We can introduce this into our expression for the flux to get the net flux of A at steady state as shown here. Now, in the gas phase, we can do a shell balance, and between Z and Z plus delta Z, somewhere in here in the gas phase. And what we would find is there's no chemical reaction in the gas phase. The reaction is occurring at the catalyst surface. And so in the gas phase, there's no chemical reaction. If it's at steady state, then the flux can't vary with position in the boundary layer. And so you'll just emphasize that the reaction doesn't enter the mass balance at this point because it's only in the gas phase, and it's only occurring because the mass balance is on the gas phase, and the reaction only occurs on the solid surface and does not occur in the gas phase. And so we can now combine the mass flux and mass balance expressions as shown here. And if temperature and pressure are constant, which is then C and DAB will typically be constants and can come outside the derivative. I've just shown you in the previous example with the spherical particle how we can introduce temperature gradients if we know how the temperature varies from the catalyst surface out into the well-mixed reactor. We can account for temperature changes, but here we're going to focus first on the mass transfer results in the simplest case where it's at constant temperature and pressure. One boundary condition is at the edge of the boundary layer, the concentration of A is going to be the bulk average mixture concentration, or the mole fraction of A will be XA0. For the other boundary condition, we need an expression for how the concentration of A, how the concentration of A or how the flux of A is given at this catalytic surface. We know A is coming through the boundary layer to get to the surface to undergo chemical reaction. And for convenience, we're just going to use a simple first order model that the flux of A at the catalytic surface is equal to rate constant times the concentration of A in the gas phase at the catalyst surface, what I'm calling Z equals delta. We can write that gas phase concentration as the total molar concentration times the mole fraction of A. Now, in reality, if this is a heterogeneous chemical reaction, what is happening typically is that the gas phase concentration of component A at that surface, the gas is adsorbing onto the catalyst particle surface, and then once adsorbed onto the surface is undergoing the dimerization reaction. There would typically be an equilibrium between the amount of A that's adsorbed on the surface at any time and the amount of A that is in the gas phase just next to the surface. So we're talking about the amount of A, the concentration of A or mole fraction of A that is in the gas phase just next to the surface. There would be a separate analysis to carry this further that would relate this concentration to the gas phase, to the concentration of A adsorbed on the surface, and you would use something, for example, like a Langmuir isotherm to calculate that. And I'll show you how to do that a bit later on, but I don't want to get bogged down in those details for now. And so with these boundary conditions, we can solve the differential mass balance to get an expression for the concentration profile that is shown here. And to use it for practical calculations, we have to determine the flux. The flux of A we're going to get at the edge of the boundary layer, because that's where we're going to try to connect it up with the mass balance on the overall reactor. And so I'm going to be evaluating that at Z equals 0, and I can use this expression to calculate this derivative, and you should verify that this is a result. It's an implicit relationship now for the flux. The flux appears on both sides of this equation. K is the reaction rate constant, delta is the boundary layer thickness, XA0 is the bulk concentration of A, DAB is the diffusion coefficient. And now I want to look at a couple limits on this. And the limit when the reaction rate becomes fast relative to the flux of A, that is, in the limit where K becomes large relative to the flux of A divided by the total molar concentration, we can expand the numerator of this expression as shown here, and you should verify that this is in fact the case. And so this expression gives the combined effect of reaction and diffusion on the flux of A, and the dimensionless parameter that characterizes the effect of reaction kinetics on overall mass transfer is this grouping of terms dAB over the reaction rate constant times the boundary layer thickness. The reciprocal of this, that is the reaction rate constant boundary layer thickness over dAB, is the so-called second Dom-Keller number, and it is a dimensionless group that characterizes the relative rate of surface reaction, heterogeneous surface reaction, to diffusion of components through a surrounding gas or liquid phase to feed that surface reaction. So when this grouping of terms is large, it means that either the diffusion coefficient is small or the reaction rate constant is large, or the thickness is large and the reaction is much faster than the diffusion. When it's small, it means the reaction is slow. The thickness of the boundary layer is thin, the diffusion coefficients are high or some combination, and then diffusion is faster than chemical reaction. We can consider the case where the chemical reaction at the surface is infinitely fast, that is, where K approaches infinity. And in this case, when K goes to infinity, the term here on the bottom goes to 0. And we're left with the result that is shown here. And what this shows is that just because the surface reaction is infinitely fast doesn't mean that the flux of A goes to infinity. What's happening in this case is as that surface reaction gets faster and faster, the flux becomes more limited by diffusion through the gas phase to reach the surface. And this corresponds to the limit where the rate of conversion of A to B at that catalytic surface is entirely limited by the ability to bring A to the surface to undergo reaction through that diffusion boundary layer. That is, the reaction is in series with the diffusion processes, and when the reaction becomes fast enough, the mass transfer is governed only by diffusion through the boundary layer, which is shown here. In the limit where the concentration or mole fraction of A is small, that is, where the convective effects or frame of reference effects are small, look at the result that you get and how simple it is. The flux of A is just the concentration, molar concentration, diffusion coefficient, times the concentration difference in A across the boundary layer divided by the boundary layer thickness. If we multiply C times XA0, we get the concentration of A at the edge of the boundary layer. All of the A is consumed by the chemical reaction at the surface of the catalytic particle. Result is in the limit of infinitely fast kinetics, and then the flux is given by the simplest expression you can imagine, diffusion coefficient times the concentration difference divided by the thickness of the region over which A is diffusing. This result will show up over and over again in mass transport. It is a primordial result that flux goes according to diffusion coefficients times concentration gradients over the distance over which diffusion occurs. And we'll see this occurring again and again and again. It is exactly the result we get if the convection or frame of reference effects were negligible and the reaction were so fast that the concentration of A at the surface was 0. And to see that this is so, you can solve the differential equation that's shown here, subject to the boundary conditions that are given. You'll get exactly this result. I think at this point we're very close to the time for this lecture to stop, and I think I'm going to stop it here before I introduce the beginnings of a new topic. So this will be the end of this lecture.